Welcome to today's tutorial on multi-class ECG classification, perceptron versus multi-layer perceptron in MATLAB. I'm Shanti. I work as a senior online course developer at MathWorks. You may know us as makers of MATLAB and Simulink, which are our core products. MathWorks is a leading developer of mathematical computing software for engineers and scientists. Our tools are used extensively across a range of industries, including aerospace and defense, automotive, biotechnology, and communication. In this session, first we'll begin by defining an engineering problem. Next, we'll explore a solution to this problem, walking through the key steps and considerations. After that, we'll guide you through getting started with MATLAB Online, ensuring you have the tools you need to follow along. After that, we'll move into a hands-on activity where we'll implement both perceptron and multi-layer perceptron in MATLAB. I encourage you all to follow along with me during these activities. We'll end the tutorial by summarizing the key takeaways and a Q&A session. If you have any questions, post them in the chat. We'll try to address them then and there, or we'll take up those during the Q&A session. I would like to emphasize here that today's tutorial focuses on using MATLAB to develop a neural network model without going too deep into theory. So talking about the engineering problem we are trying to solve today. So our central question is to develop a neural network model to classify ECG heartbeats into three classes. We have defined here three classes: normal, premature ventricular contraction, and atrial fibrillation, using two extracted features, QRS width and RR interval. Just to give a brief on what these features are, the image here shows a typical ECG waveform. So the main components labeled here are the P wave, QRS wave, and T wave, which represent different phases of heart's electrical cycle. The QRX complex marks the rapid depolarization of the ventricles, and the RR interval is the time between two consecutive R waves, indicating one complete heartbeat. So in today's problem, the QRS width and RR interval are the two features we are considering today to train the neural network model. So in practice or in real world scenario, there is considerable overlap in QRS width and RR interval values among the different heartbeat classes due to many reasons. It can be due to physiological variability or due to the presence of noise in real world ECG recordings. So this makes it difficult to draw clear boundaries between these classes while doing signal classification. Therefore, while developing a neural network model, it's crucial to design a robust multi-class classification approach that can effectively handle these overlaps and is suitable for real-time monitoring scenarios. So this is the engineering challenge we'll be addressing in MATLAB today. So talking about the general approach for any signal classification problem for that matter, it involves importing or generating the signal, extracting features from the signal, which can be any statistical features or domain-specific characteristics, such as peaks, intervals, or frequency components. And these features are then fed to a classifier, such as a neural network classifier, which processes these features and assigns a signal to one of the output classes. So we will reach the solution to our engineering problem today by going through various steps. First, we will generate the required signals for both training and testing our neural network model. Next, we'll train and evaluate a simple perceptron model, which is a single layer neural network. This model helps us establish a baseline for classification performance. After that, we move to a more complex architecture, a multi-layer perceptron or MLP. With its multiple layers, we'll analyze if the MLP is capable of capturing more intricate patterns in the ECG data. Finally, we'll assess the performance of both these models using matrices like accuracy or precision and recall. This allows us to determine how well our models can classify each type of heartbeat, guiding us towards the most effective solution. So as a first step to solve the engineering problem, we'll get started with MATLAB Online. All the registered learners to this NPTEL course, Neural Networks for Signal Processing, have access to MATLAB Online and have access to these set of products. So for today's session, I have a work live script for you to practice along with me. I'm sharing the work script in the chat. So the work script has placeholders to enter the code which we will do together during the hands-on activity. Please download the work script to your device. I'm sharing the work script in the chat. Please download it to your device. So during the session, I'll post the codes in the chat so that it is easier to follow along with me. And at the end of the session, I'll share the solution live script for your future reference. So next we'll see how to access MATLAB Online provided for this NPTEL course. So for that, go to the NPTEL course page, Neural Networks for Signal Processing. Go to the main page for the NPTEL course, Neural Networks for Signal Processing, and come down to the MATLAB section. So on the left, in the course outline section, you will find a MATLAB option. Click on that, where you will get two options, MATLAB Access and MATLAB Training. Click on MATLAB Access. So here you will see a series of steps to access MATLAB Online for this particular course. So first step, if you don't have a MathWorks account, you need to create one. So in the step 1, the link provided here, you can quickly create one by clicking this link in step 1. Once the account is set up, you can click on the link from step 2, which says Access MATLAB for your NPTEL course. So once you click on the link in the step 2, you will redirect to the Access MATLAB Online page, where you can click Access MATLAB Online. This will take you to the MATLAB Online page. The URL should say matlab.mathworks.com. I hope everyone could open MATLAB Online. Now click on Open MATLAB Online. So now we have opened MATLAB online. Now we will see how to upload the work live script which we downloaded some time back to the MATLAB drive. For that, on the left side, the files pane, right click on the files pane and you will see an option called upload files. Click on upload files. Now locate the file which you downloaded some time back, which says workscript_nptel perceptron versus MLP. So select that work script and click open. So once the uploading is completed, it will show 100%. Once this message appears, you can click OK. If you have any queries on how to access MATLAB or how to upload the work script to the MATLAB drive, please share in the chat. So now we'll open the work script which we uploaded now. For that, double click on the work_nptel perceptron versus MLP file. You can double click to open the work script. So once you open the work script, it's a live script. So for those who are new to live script, live script is an interactive script where we can embed code snippets, text and images in one environment. To make you familiarized with the live script environment, we have tabs like home, plots, apps, live editor on top of the live script environment, which is called toolstrip. On the left, you can see two panes, which is files pane and workspace pane. For now, you can reduce or minimize the files pane and workspace pane so that the screen is big enough to write the code and analyze the results. So this is the work script which we will be working in today's session. So for easy navigation to each section, the table of contents here is linked to different section in the live script. So you can easily navigate to a specific section by clicking on a heading in the table of contents. So just to reiterate the engineering problem we are trying to tackle today. So our engineering problem is to develop a neural network model to classify ECG heartbeats into 3 classes. So we have 3 output classes: normal, PVC and AFIB. So we have extracted 2 features. We are considering 2 features of the ECG signal here. The first feature is QRS width and the second one is RR interval. So to achieve our objective and to address the engineering challenge we'll go through 5 steps. So first we will generate the training data and next we will generate the testing data to test our accuracy of our neural network model. And then we will move ahead with training and evaluating the models. First, we'll start with simple perceptron, and then we'll go ahead with the complex multi-layer perceptron. And finally, we will compare the models. So these are the steps which we'll be doing to address our engineering challenge today. So as a first step, we'll generate the training data. So the task here is to generate synthetic training data for 3 heartbeat types using Gaussian distribution and label the data appropriately and visualize the feature space to inspect class separation and overlap. So here, since real ECG data may not be readily available, we are going ahead with generating the training data for 3 heartbeat classes, and we'll be considering 2 features, QRS width and RR interval. And each class here is generated with different means and variations to mimic physiological variability and ensure some overlap, making the classification problem realistic. So as a first step, let's generate the training data using Gaussian distribution or using random Gaussian distribution function. So for that, for reproducibility, we will define the random number generator seed and set it to number 42. So I am posting the code as well in the chat for your reference. So the first line is to set the random number generator seed to 42. So why this setting the seed is important is because this allows you to get the same random number every time you run your code. So which is important for debugging, testing and sharing results. So that's the reason we are setting the random number generator seed to a particular number. So for today's example, we have set it to 42. Now we are going to define the training size. So let's call the training data size as ntrain and let's define it as 100. So the training size is 100. So that means we are going to generate 100 samples for each heart condition. Now, as I mentioned before, we are considering 2 features here, QRS width and RR interval, and we have 3 different classes. So we will generate 3 different classes with these two features and call it as normal train, PVC train and AFIB train. So what we have done here is we have generated 3 classes, 3 ECG classes with 2 features, QRS width and RR interval. To make the features closer to the realistic value, have chosen normal train QRS width as centered around 0.8 with a small variation and RR interval around 0.8. And PVC, since it's a heart condition, it will have more variations in the QRS width. So I have centered it around 1.0 and the RR interval around 0.6. And AFIB, which is again another abnormal heart condition. So here the variation is set to 0.09 and centered around 0.9. And the RR interval is around 0.5, both with moderate variation. Now we are combining all these features from all the 3 classes to a variable called features train. So features train equals is a matrix which has all the features from all these 3 classes. So now that we have defined the features for each ECG class variables, now we will assign labels for these 3 classes. So for that, we are considering that normal class is 1 with value 1 label and PVC is value 2 and AFIB condition is value 3. So all the normal ECG class signal will have a label of 1. So let's assign these labels and call this labels as labels train. So we need labels as same number of how many signals features we have. So we have total n train signals for each of the ECG classes. So those many labels are needed. So we have defined the label for the first class, which is normal class. And then now we are defining or assigning the label value 2 for the second class. So once off, the same number we have n train. And the third class with a value, with a label value 3. So we have assigned the labels accordingly as 1, 2, 3 for the specific ECG class. Now the next step is to convert these labels into one hot encoded format. So in MATLAB, the function to convert the labels into one hot encoded format is demi variable, demi var. So let's define the labels, the new format as labels train one hot equals, the function here is demi var, which means demi variable, and the input to this demi var is what is the conversion, which labels we need to convert to this new format. So it is labels train. So after executing this particular line of code, demi var, what happens is it returns a matrix containing zeros and ones. So generally for multi-class classification, one hot encoding is a standard way to represent the target output for each training example. So after we define the training data and assigning labels to our training data set, the next step is to visualize the training data set. So I have already written the code for visualization. So I have used here a scatter plot to visualize the features in all these three classes. So let's run this particular section. So to run a particular section in LiveScript, you can locate the option Run Section on the tool strip. So click on Run Section button in the tool strip. So let's analyze the result. As I mentioned, after converting the labels to one hot encoded format, it will be a matrix of ones and zeros, and it will have as many columns as how many classes we have. So for example, here we have 3 ECG classes, so it has 3 columns, and the first column corresponds to the first class, which is normal, and the second class corresponds to the PVC ECG class. And if we analyze the figure, the scatter plot for the training data set, we can see the features is being visualized here, and this visualizes how the 3 classes are distributed, and there is a noticeable overlap which indicates a perfect separation is unlikely, especially for linear classifiers. And also we can see that the later 2 classes, PVC and AFB, has pretty overlap in the features. So we need to choose a robust classifier to classify these 3 classes into separate or identify these separate classes. So now next step is to generate the test data. So similar approach how we generated the training data set, the same procedure we will follow here. First thing is to set the testing size. So we will define the testing size as 30, and let's save that testing size in n test equals 30. So that means we have 30 testing data for each class. And similar way how we selected mean and variance for each of the ECG class for the training data set, same procedure or same value we will consider here as well, and same features QRS width and RR interval. We will name these three signals as normal test, PVC test, and AFIB test. So we have chosen here same, as I mentioned, same value for variance and mean, so that it is a clear representation or representation of how we did for the training data set. Now we will combine all these features from all the three classes to a feature matrix, which is called features test. So this features test matrix has test data from all the three classes, ECG classes. So once we generate the signal with the specified features, QRS width and RR interval, the next step is to assign labels. So for assigning labels, we will assign value 1 for the first class, normal class, 2 for PVC class, and 3 for AFIB class. Let's call that labels as labels test. So to assign variables, we will call labels test ones of n test comma 1, because all the labels should, the label size should be same as that of the signal data size. So the size of the testing data set is stored in n test. And now the next step is to convert these labels into one hot encoded format. So for that we will use the dummy var function, and let's save that to a variable labels test one hot. The function is dummy var, and the input is the labels which we need to convert. So labels test. So this again will be a matrix of zeros and ones with each column representing each class. Now we'll visualize the test data set to check if it is similar to the training data set, which has the overlap, so that it is comparable to the real ECG signal data set. Let's run this section. So here, after analyzing the scatter plot, so this allows us to visually inspect the distribution of test points, and the test data clusters is overlap with the regions occupied by the training data, confirming that the test set is a fair sample from the same feature space. And also this ensures that our subsequent model evaluation will accurately reflect the classifier's ability to generalize new unseen examples. So after step 2, we have our training data, and we have our testing data and the required labels. Now we'll move on to the next step of training and evaluating a simple perceptron model. So in this step, we'll start with a simple perceptron, which is a classic linear classifier. And since our problem is a multi-class problem, meaning we have 3 ECG classes, we uses the one versus all strategy. So that means we'll train a separate perceptron for each class. So where each model learns to distinguish its target from all other classes. So in the next step, we are going to train 3 separate perceptron since we have 3 ECG classes using the one versus all approach, and we are going to make predictions on the test data set we generated and also compute the classification accuracy. So for that, first let's define a cell array to hold these 3 perceptron models. So let's call it as nets equals cell with a size of 1, 3. So we are defining a cell array to hold the 3 perceptron models. Next, we will define the number of epochs for training. We are saving that to a variable num epochs, and we are setting that value to 500. So now what we have done is we have here a cell array nets which is created to hold 3 perceptron models, and the variable num epochs is set to 500, which determines how many times each model will be trained on the training data. Now we need to define a loop which runs for all these 3 ECG classes. So here we have 3 classes. So I have already defined a for loop for k equals 1:3. So each perceptron, so 3 perceptron models will be trained for each class separately. Now let's create a perceptron model. For that, we will save it to a variable called nets, and it will get updated for each iteration. Let's call it as nets of k. To create a perceptron model, the function is perceptron. Now we will set the epochs to the value which we defined, which is 500. So for that, we need to set the training parameters for this perceptron. So for that, we will write the code as nets of k dot train param dot epochs equals the number of epochs, which is 500. So in this line, we are setting the number of epochs for our perceptron model. Now, after creating the perceptron model and setting the training parameters, now the next step is to train the perceptron model. So for training the perceptron model, the function in MATLAB is train. So we will use the function train, and the first input is our perceptron model, and next input is our data set features train on which we want to train our perceptron model, and then third input is our labels of the training data set, which is saved in labels train 1 hot. So what we have done, we have created the perceptron model. We have defined the number of epochs. We have set the number of epochs to the perceptron model, and we have returned the code for training the perceptron model. Now, the next task is to do the prediction on the test data. So for that, we will initialize predict scores underscore test one variable to initialize to store the prediction scores for each class. So what happens here is the loop iterates through each perceptron using it to predict scores for the test features. And the results are stored in the corresponding column of predicted score test. So we will write the code to calculate the prediction score in the loop which iterates from k equals 1 to 3. So prediction score test. Each class prediction score test is saved in each column for the test data set. So after calculating the prediction score, we will determine the predicted labels. So for that, we will use the max function to calculate the maximum score and save the corresponding label, predicted label, to the variable predicted labels test. Now we will run this section. Let's run this section by clicking on Run Section button. It will take some time to complete the training because there is 3 perceptron model to train. It will take around 1 minute to complete the training. Let's wait for that. So in step 3, we have trained 3 separate perceptron, and now we are waiting for the results to appear to complete the training and see what are the prediction score and also what is the classification accuracy for our test data set. So you can also parallelly see the training progress here in this chart. Where you will see the training results, how many epochs is completed, and what is the progress, what is the elapsed time, and the performance for each perceptron. So the first perceptron model is being trained. Training is completed for the first perceptron. The second perceptron training is in progress. Since we have set the epochs value to 500, it will take some more time to complete the training. If the training is completed for you, you can share your test accuracy results in the chat. So I have a question in the chat here. What does this one by one network mean in the nets celery? So one by one network here means that we have uh, one network model, one layer, single layer perceptron model designed for each class. Since we have three columns here, each network, each perceptron network is, or the training options is getting saved in each column. Uh, let's let's proceed to the step 4, and we'll come back to step 3 and analyze the results. What was the test accuracy once the execution is completed? So as a next step, since we used a single layer perceptron for our ECG classification problem. Now let's try a multi-layer perceptron or an MLP for training, and let's evaluate how this model performs when compared to the single-layer perceptron. So multi-layer perceptron is a type of feed-forward neural network that can learn complex nonlinear decision boundaries. So unlike the linear perceptron or a simple single layer perceptron, the MLP can model overlapping classes more effectively by using hidden layers and nonlinear activation functions. So let's see how the performance for an MLP looks like for our multi-class ECG classification problem. So for that, let's first define the hidden layer size for the MLP. So let's save or save the hidden layer size into variable hidden layer size equals 10. We are considering 10 neurons here uh, per hidden layer. So first we have defined the hidden layer size as 10. Now we will define a pattern recognition neural network using a function called patternNet. So let's save this in a variable MLP equals patternNet with the hidden layer size we already defined. So this line of code returns a pattern recognition networks as feed-forward networks that can be trained to classify inputs according to the target classes. Now let's also set the training parameters like how we did for single layer perceptron. We will define the number of epochs to same value, which is 500. So MLP dot train param dot epochs equals num epochs. So what we have done, we have first defined the hidden layer size, and then we have defined a pattern recognition neural network with the hidden number of layers or size we have defined in the previous step. And now we are going to set the training parameters where we have used the same number of epochs as before. Now, the next step is to train the MLP. So we will use the same function, train function, for training the MLP or multi-layer perceptron model. MLP equals, the function is train with inputs. First input is the network model, which is stored in MLP. And the second input is the train features. And the third input is labels. The trained dataset labels. So we have used the train function as before to train the MLP network. And as before, how we calculated the prediction score on the test data, the same set of code is being used here, only with the difference of the model we are choosing. So earlier we have chosen a single layer perceptron. Now we have replaced that with MLP. So in this line of code from 114 to 116, where we are calculating the prediction score on test data, the max function is used again here to identify the index of the highest score for each test sample, and the corresponding predicted label test is being saved in this particular MLP predicted underscore labels test variable. And the predicted labels are here then transposed to match the original format. And as a last step, we have calculated the test accuracy for the new MLP model. So for calculating the test accuracy, MLP test accuracy equals sum of the tested, the predicted labels, which is equivalent to the labels test divided by length of the labels test. Let's see what is the progress on our single layer perceptron training. Yeah, so we are in the training for the third perceptron model. 260 epochs has been completed. Uh, yeah, we'll wait a couple of more minutes to complete the training and analyze the results. So the training time for the model depends on various factors. It depends on the number of epochs you are selecting. It also depends on the data set. Uh, if there are like more number of data samples, or if the epochs rate is more, it will take more time to train the model. So from this neural network training GUI, you can directly view the network diagram which you have modeled, and also you can see the training plots, performance, training state, and confusion metrics. The training is almost completed. We are almost reaching 500 target value. And the results here is expected to show the test accuracy results, and also to visualize the network diagram we just modeled. So we are expecting a network model diagram for single layer perceptron after completing this particular execution for this section. So there we will see how many layers are there, or are there any hidden layers for a single layer perceptron. So we have finished the training, and we can also see the network diagram here for the single layer perceptron. So here we have input layer, and there is the weight and biases, and also an output layer. So here you don't see any presence of hidden layers in a single layer perceptron. Now let's see what is the training accuracy or testing accuracy we calculated for the single layer perceptron. So we got the result as 66.67%, which is kind of a moderate value, and we can conclude that single layer perceptron is not well suited for multi-class classification. And also if there are like overlaps in this data set, it's not well recommended to use a single layer perceptron. Now let's go to the step 4 and run the section which we have already completed coding, where we used multi-layer perceptron. Let's run this section and analyze the results here. So here we have used a multi-layer perceptron. That means there will be a hidden layer to it, and also we are expecting the training accuracy should be, or the testing accuracy should be increased as compared to the single layer perceptron. So let's see the results we got. So this is the network model for a multi-layer perceptron, where you can see a hidden presence of hidden layer here, and we have considered here only one hidden layer because that is what we have defined for the MLP, and also we have assigned 10 neurons for this hidden layer. Now let's analyze the accuracy for testing accuracy for MLP. So if you see the testing accuracy for MLP, it is around 91.11%, which is pretty good accuracy for a multi-class ECG classification problem. So this higher test accuracy compared to the perceptron demonstrate that the advantage of nonlinear modeling, especially in the presence of overlapping classes. And if the MLP significantly outperforms the perceptron, it suggests that the decision boundaries between classes are indeed nonlinear in that particular problem. And also it validates the use of more complex models for challenging multi-class classification tasks. So till now what we have done is we have we have considered an ECG data set with two features, the QRS width and QRS and RR width and RR peak duration. And we have compared two models, single layer perceptron, and we have seen the testing accuracy when that model was used, and we have also used multi-layer perceptron, and we have tested the testing accuracy for that model. Now as a next step, we will compare those two models, the single layer perceptron and multi-layer perceptron, with a different set of visualization. So even though overall accuracy is informative, a confusion matrix is something that reveals more details about model performance by showing how predictions are distributed across actual and predicted classes. So the confusion matrix is kind of visualization which helps to identify which classes are commonly correctly classified or which classes are commonly confused. So let's generate and visualize the confusion matrix for both the perceptron and the MLP classifier we used. I have already returned the code for displaying the confusion chart. So for displaying the confusion chart in MATLAB, the function is confusion chart, and we need to give mainly two inputs, which is label test, which is our true class, true labels, and what is the predicted label test or train for the after modeling. So here we are displaying the confusion chart for the test data set for the perceptron model, and I have also given the name value options as I have given a title for the confusion chart, perceptron test confusion matrix, and also I have given the features of row summary as rows normalized and column summary as column normalized. So these two options, row summary and column summary, ensures that the matrix displays normalized values, making it easier to assess the model performance across different classes. So the same function is used here also to display the confusion chart for multi-layer perceptron. Let's run this section and see what are the results. So here we got the confusion matrix or confusion chart for the perceptron model. So here in the confusion chart, the row represents the true class and the column represents predicted class. And if you remember, the one label was is mentioned for normal class, 2 for PVC, and 3 for AFIB. And you also might have remembered that the second and third class had more overlaps in the defined features. So when using perceptron, it is misclassified mainly the second second ECG class PVC, which is misclassified as the third ECG class. So that's why the accuracy was around 66 or 67% for the single layer perceptron. And for the multi-layer perceptron, if you analyze the confusion chart, the first ECG class, which is normal class, it's been correctly classified. 30 were the number of test data sets we have for each class, for each ECG class. It's been rightly classified. And for the second class, 26 ECG test samples is being correctly classified or predicted correctly as PVC class, and 4 is being misclassified. And same goes with the third class as well. 26 is being correctly classified and 4 is being misclassified. So after comparing the accuracy and after comparing these two charts for these models, perceptron and MLP, we can see that MLP reduces confusion between overlapping classes compared to the perceptron. And the diagonal values, and there are high diagonal values for MLP confusion chart and low of diagonal values, indicating strong performance for multi-class problems. So here the confusion matrix, as I mentioned before, provided a detailed class by class comparison, allowing for targeted model improvements for further analysis if needed. So hence we come to the end of our tutorial. So here we compared two models, perceptron and MLP, and we took an example of ECG classification. There are some additional resources also mentioned for your future reference. You can refer to that. I'm sharing the solution live script in the chat for your reference. All the details of the problem which we solved today is being mentioned in the solution live script. So to summarize, we had our engineering problem was to develop a neural network model to classify ECG heartbeats into 3 classes using two extracted features, QRS width and RR interval. And to achieve our objective and address the engineering challenges, we went through a series of steps and compared the simple perceptron and multi-layer perceptron. And these were the final observations. So when you compare the perceptron and multi-layer perceptron, the model type, we can say that perceptron is a linear classifier which has single layer, and multi-layer perceptron is a non-linear classifier which has hidden layers and activations. And when you talk about the decision boundary, perceptron normally has a straight line or a hyperplane, but the multi-layer has a curved decision boundary, making it suitable for non-linear boundaries problems. And if you compare the complexity, we can say that perceptron is has low complexity while modeling and training because of few parameters, and the complexity for multi-layer perceptron is higher because there are more parameters to train. And when coming to the accuracy, for the test data set, for perceptron, we received a moderate accuracy, which there was a limitation for overlapping features. And also for multi-layer perceptron, we received a higher accuracy. That means it can handle an overlapping classes better than perceptron. So here we come to the end of the session. I'm sharing the solution live script in the chat for your reference. You can download that as well and refer uh, to the engineering problem we solved today for your future reference. Thank you all for joining.